In this lesson, we're going to be discussing how to describe motion in space. So we talked before about how we could describe the curve or any particular curve as a vector function called r of t. And every t value would be associated with a particular vector that extends from the origin. In addition, we could look at the velocity vector that would end up being the tangent, or it would be showing the direction of motion, but it would be tangent to the curve. And if we divide that velocity by its magnitude, we end up getting the unit tangent vector. And that tangent vector is 1 unit long, unit tangent, and it'll always be pointing in the direction of motion. Now, sometimes we're interested in determining how long a curve actually is, or how long a segment of a curve is. So if we were to take a look now at a curve in space, let's say that we have this particular curve. T equals 0 is going to be the starting point at some base point, and we're going to define S from now on as being a length of some arc or length of some curve. So if you were to picture this black curve as a string, and you were to pull that string nice and tight, you could think of this as a number line. And you could really scale our number line, or our curve, very similar to a number line. So you could say that this would be S equal to 1, and this right here would be S equals 2. By the time we get out to here, this would be S equals 3. And you could even extend backwards. You could say that this is S equals -1 if it's before the base point, and S equals -2. And you can see what I'm trying to do is actually make sure that these are equally distant. So we're scaling this very similar to a number line. Now we're going to be getting there at different t values, but what we're interested in doing is finding out what the length of a curve is between any two t values. Well, I'd like to derive the formula for how we could find the arc length of some curve. Now we did this actually in Calculus 2, and we came up with a particular formula. But because we I'm not going to refer to that formula because the curves in multivariable calculus are functions of t. And so they're parametric curves. So if we want to be able to describe arc length parametrically, we need to think about smaller little segments. So let's think about how we could find the length of just that piece. All right, well, let's call that the change in S. Okay, well, we know that by the Pythagorean theorem, we could draw a triangle here. And recognize that this right triangle has a change in X and it has a change in Y. Now I'm going to derive this just in 2 dimensions and use what we also learned about distance in the beginning of this class about extending it into 3 dimensions. So let's keep in mind something important here to realize that this means that ds squared is equal to dx squared plus dy squared. Okay. But if I want to find the change in S, then the change in S is going to be the square root of that. So that would mean the change in S is equal to the square root of the change in X squared plus the change in Y squared. Okay, but remember that S is supposed to be a function of t because I'd like to show that as t increases, so does my S, so does my arc length. So what I'm going to do here is we're going to try to figure out how we could find what S is. Well, if this is the derivative of S, eventually I'm going to want to have to integrate in order to find S. So the integral of ds is S. But we're not ready to integrate yet because we don't know what to integrate with respect to on the right side. So we're going to do a little bit of fancy algebra here. So why don't we think about doing this? Why don't we think about dividing everything by dt squared? Okay, so let's take dx squared plus dy squared. And what we're going to do is we're going to divide everything by dt squared. It may seem a little peculiar right now, but just bear with me. But notice that this has changed things because I can't just divide everything by dt squared unless at the same time I multiply by dt squared. So now when I've multiplied and divided by dt squared, I haven't really changed the equation. What's in purple is still the same exact equation. But there was a benefit of doing this, because this shows us that ds is equal to the square root of, since both quantities dx and dt are being squared, I could rewrite this as dx dt squared. And for the y terms, I could also do the same thing. I could pull out the square and rewrite it as dy dt squared. But we're not quite done, because what I'd like to also do is recognize that this dt squared is being square rooted. So the square root of dt squared is simply dt. So I could pull out that dt, and now notice that we're actually able to integrate both sides. If I now integrate the left side, and I integrate the right side with respect to t, we now have our formula for arc length. Our formula for arc length is simply s of t, s, the integral of ds, I'm going to call that s of t, is equal to the integral of the square root of the derivative of x squared plus the derivative of y squared dt. And this formula will now allow us to be able to find the arc length of any particular quantity between any two t values, from t1 to t2. So I could find the integral, or I could find the arc length between any two t values simply by applying this formula. And to take it a step further, this is simply in 2 dimensions. If I now take it a step further in 3 dimensions, we should be able to see that the arc length formula is really no different. S of t is equal to the integral from t1 to t2 of the square root of, and keep in mind that we have a position vector. So this is assuming that we are given, okay, before I write that formula, this is assuming that we're given a position vector called r of t. That's always equal to some function of f in the I direction plus some function of g in the j direction plus some function of h in the k direction. What this x and y were saying was that those were the x and y components of that vector. So that would actually, instead of saying dx dt, why don't we refer to that now as f prime of t squared plus, and instead of referring to this as dy dt, why do we refer to this as g prime of t squared? And now when we add our third component, we finally have h prime of t squared, and this is with respect to t. So from now on, this is how we're actually going to be finding the arc length in 3 dimensions in multivariable calculus. Now, Something about this arc length formula that's pretty amazing. I'd like you to recognize that if this is the function r of t, our position function, then I could find our velocity function by just simply taking the derivative of each of those components. Now notice what is being squared in each of these components of the arc length formula. It's the components of velocity. More importantly though, if I were to find the magnitude of velocity, then the magnitude of velocity is simply going to be the square root of f prime squared plus g prime squared plus h prime squared. And notice that's the integrand. That's the quantity that we're actually integrating. So it turns out then that what we are doing in order to find arc length is going to be equal to this scalar function called s of t, which is simply saying the distance traveled over a certain period of time is equal to the integral from some base point to some t value. And I'm going to change the color on that just so we could see here that when we refer to this t value, it's basically where we are stopping. So when I start at some base point of t0, and I want to find the arc length until I get to some t value, let's say t equals 3, all I'm doing here is integrating the magnitude of velocity. So notice that when I integrate that magnitude of velocity, let's think about what that magnitude of velocity is saying. Velocity is telling me the speed and direction of my particle or my roller coaster or my bee or my fly or whatever it is that's moving through space. The magnitude of that vector is telling me the length. The length is nothing more than the speed. So when I refer to this magnitude of velocity in 3 dimensions, that's actually our speed. Now let's look at this. It looks like I'm multiplying my speed times my time, my change in time. When I look at rate times time or speed times time, and I add up all of those speed times times, that should give me a distance. Distance equals rate times time. So that's why the arc length formula is nothing more than just integrating speed. So when we integrate the speed of a particle or the speed of some object, we simply get an arc length. Let's take this a step further now and say, what if we were to take the derivative of my distance? Or in other words, what's the rate at which my distance changes? So let's write out what that represents. This is the rate at which distance changes. And to be more specific, it's the rate at which distance changes as time changes. And so in other words, ddt of s could also be written as ds dt. Now you might also notice that I changed this variable of t to another variable called tau. That's just a Greek letter for t. The reason is t is the independent variable. T is where we're stopping. So when we say s of 3, then we're saying what is the distance traveled until I get to 3. So this is the variable of integration. This is just going to be some other variable, okay? But don't worry about that too much. Notice that if s of t is equal to that integral, taking ddt of the integral from t0 to t cancels the integral. That's the fundamental theorem of calculus. So all that integral on the left side is equal to is simply the magnitude. So that's simply equal to the magnitude of v of t. And when we take that magnitude, these two things are equal, which is why that's nothing more than speed. So this is a really important actual relationship because it shows us that when we take the derivative of my arc length with respect to time, that is nothing more than velocity. So we can actually take a look at this graphically now. Look at our position curve, which remember we referred to as R of t. Then we can see that what if we want to find the distance between two particular t values? Let's say that we start at t0 at some base point. It doesn't matter where that base point is. It's just basically wherever you're beginning. Let's say you're starting at t equals 2. We just happen to here be starting at t equals 0. And we're extending that until this point P that's occurring at some other t value. That's what we refer to as t0 and t on our limits of integration. We're now just saying we're trying to find the arc length, which is the distance traveled from t0 to t. That distance is referred to as s, or more specifically, s of t. So this is a really important distinction. R of t is a vector function because the output at each t value is giving me a vector. S of t is a scalar function because each value of t is giving me a distance or a length. And that's a really important distinction between R and S. In multivariable calculus, we deal mostly with vector functions. Vector R, that's a vector function. Vector V is a vector function. Vector capital T is a vector function. But notice that the function S of t is actually a scalar function. One aspect of this that's pretty interesting and important to recognize, and that's that, notice that the speed is never equal to 0 for a smooth curve. That would mean that the particle stopped. But for a smooth curve, we recognize that the particle is constantly increasing because the velocity is constantly going to be increasing, moving forward rather, okay? Well, if the speed, which remember is the same as ds dt, is never equal to 0, then that must mean that that integral, that derivative rather, that ds dt, is going to also be greater than 0. The speed will be greater than 0. It'll be positive, obviously. But if the speed is positive, that means that the derivative is positive. And when the derivative is positive, that means that the original function is increasing. So just to show us what's going on here, we know that the distance from some base point to some t value is always increasing simply because the derivative is always greater than 0. Now that's a pretty interesting thing to recognize, but we're going to use this fact that ds dt is going to be the speed to our advantage when we start this next idea of how we can look at how the position vector changes as a different variable is input. I said before that we're going to want to really get used to handling Leibniz notation. And remember, Leibniz notation is when we deal with the ddt, ddr, drds, drdt, and so on, dy dx. So we've got to realize that the velocity vector, which we call v of t, is the change in position over time. It's how quickly is the position changing as time ticks on. So you can picture this as starting a stopwatch and figuring out when that stopwatch starts, how quickly is my position changing? Let's say I'm running a race as my time increases. That would be referred to as velocity. But sometimes instead of finding dr dt, we want to know how quickly the position changes as we move along the curve. That's a much different question. dr dt is saying, how quickly are we moving? How quickly is position changing as time ticks on? While dr ds is saying, how quickly is my position changing as I move along the track? So I'd like to just look at the diagram one more time to understand the difference between those. Notice that each of these vectors, the purple one and the orange one, are just two different position vectors. And the position vector is changing as I increase time, or I could think about it as the position vector changing as I move along the curve. So the velocity would be referring to t0, as I move from, the velocity would be saying, as I move from t0 to t, how does my position change? But what if instead of doing that, we say we've got the s values as being some length as we move along the curve here. Remember how we could look at this as kind of like a number line. Now I'm saying as I increase my distance from one to the next to the next to the next, how quickly is my position vector changing? So we're again going to do a little bit of fancy footwork here in order to figure out what the derivative of r with respect to s is. So we know that v of t is dr dt, both in orange right there. We want to calculate what dr ds is. So how could I find dr ds? Well, here's the issue. When I have r of t, notice that my independent variable is already t, so when I take the derivative with respect to t, everything is still in terms of t's. And 99% of the time, we're going to be in terms of t's. But now what we're asking is, what if we are given r as a function of arc length? And now we want to determine how quickly is r changing as that s value changes. We typically don't have a function in terms of s. So what we need to do instead is we have to convert this to functions of t. So why don't we think about this Leibniz notation as fractions? And so we could think about this as dr dt times dt ds. Because look, if I cross multiply, I'm back to dr ds. But let's look at what the significance of this is. First of all, this is a demonstration of the chain rule. If I want to find the derivative of r with respect to s, then why don't we take the derivative of r with respect to t and then find the derivative of t with respect to the variable that we need. So that's why we just applied the chain rule there. Well, that's nice because look at what dr dt is. Dr dt is nothing more than the velocity function. So that's simply v of t times dt ds. But again, that would imply that I would have to have t as a function of s. I don't have t as a function of s. Let me write that out so you can see what we're referring to. This is saying we would need some t as a function of s, which means you give me an arc length and I'll tell you the time that it took. We typically don't have that. But what we might have is s of t. So why don't we think about this a little differently again? Why don't we think about this as v of t times 1 over ds dt. 1 over ds dt is the same as dt ds. Okay, but now what's nice about this is we know what ds dt is. We just learned about ds dt. ds dt is the magnitude of velocity. So that means that what we have here is v of t times 1 over the velocity. But notice that if we combine that into one fraction, we simply get the velocity over the magnitude of velocity. So wait, that means that that's just a unit vector for the velocity function. We also learned what that is. That is nothing more than the vector t of t. So look at something really intriguing. We're saying that the velocity is simply the rate at which r is changing as time changes. But if we want to find out how is the position changing as the arc length changes, now it just turns out to be the unit vector. So I'd like to again take a look at a graph. When we describe the unit tangent vector as the rate at which my position changes as I move along the curve, we're recognizing that all it is a unit vector in the direction of the velocity. So if this green curve describes my curve r in space in 2 dimensions or in 3 dimensions, we can see that the orange vector extending from the green point there is tangent to the curve. But that might have some length of, I don't know, 10. So that's what we refer to as the velocity, the length of it being the magnitude. But notice that now we could describe the rate at which the position moves along the curve as the vector called t, which is always going to be a unit vector in the direction of the velocity. It's something interesting about these two graphs now relating to the unit tangent vector. So what I've done is I've drawn two different curves, the blue one on the left and the blue one on the right. They're both referring to some position vector, position curve called r. But I've labeled S because I want to think now about just as S increases or as the distance increases. So as I move from P0 to P1 to P2 to P3 and so on, how does my arc length increase? And you can see also that I've labeled each of the pink points approximately equal distances apart. So we could really see what's going on with the unit tangent vectors. So now what I'm going to do is I'm going to try my best to just draw some unit tangent vectors here. And I'm going to draw that to be the indicated length of the unit tangent vector. First of all, notice that it's tangent to the curve. And by the time I get to here, it would now look like this. Now I'm trying my best to make sure that these are all the same exact distance, or the same exact length rather, and that they're tangent to the curve. And by the time I get up to here, it looks like that right there would be my tangent vector. So each one of these should hopefully have the same length because they're all 1 unit long. These are all unit tangent vectors. And I'd like you to see that within 3 units of S, 1, 2, 3 units, okay, it looks like the unit tangent vector changed direction pretty rapidly. Here, at the beginning, it was pointing down in this direction. And within 3 units, look at how it moved to pointing to the right, to pointing up to the northeast, up to pointing almost, just past north. So it appears that within a small distance frame, okay, of S, T curved pretty quickly, okay? Now let's take a look at the other curve here and recognize that I can still draw my unit tangent vector, again, that being T, and now I move 1 unit away, and I'm still drawing tangent to the curve, and now that's T, still 1 unit long. Move to here, that's tangent to the curve, still T. And now we can see by the time we get to here, that's the unit tangent vector, still tangent to the curve. So now I'd like you to see the big difference between these. Within 3 units of distance, look how much that arrow's direction changed. And now on this curve, within 3 units of distance, it doesn't look like it changed as much. We refer to what we just discussed here as curvature. Curvature could kind of be thought of in multivariable calculus as an analogy to slope in algebra. Remember, slope is nothing more than just a number associated with a line that indicates how steep the curve is, or how steep the line is, or if you're talking about in calculus, how steep the curve is. So you can see that a slope of 3 would be a steeper line than the slope of 1. Well, likewise, with curvature in calculus, in multivariable calculus here, we're going to be able to recognize that a larger curvature has a bigger numeric value. A smaller curvature has a smaller numeric value. So I would assume here that this has a large curvature, while the graph on the right tends to have a smaller curvature. Okay, so notice that its length remains constant, but only the direction is changing. So the curvature is essentially the rate at which t, the unit tangent vector, turns per unit length, or per unit of length. And remember that my units of length are measured in s as we move along the curve. So the curvature is also a derivative. The curvature is nothing more than the rate at which the tangent vector turns as I move along the curve. We refer to this as the Greek letter kappa. So kappa refers to curvature, and curvature is the rate at which the unit tangent vector changes as we move along the curve. Now, since the curvature is actually a numeric value, it's not always just going to be just the rate, the derivative of t with respect to s, because that could give us a function. So instead, we've got to think about the magnitude of dt ds. It's the magnitude of dt ds because it's telling me a numeric quantity for how quickly the t value is changing as s changes. Now, I'd like you to recognize as well, very similar to when we were looking for dr ds, remember that the vector t was dr ds. This would imply that we would need the vector t as a function of s. The problem is we don't have the vector t as a function of s in these problems because we're given a position vector in terms of t that when we differentiate to find v and use that to find the unit tangent vector, we don't have it in terms of s. So we again have to do a little fancy footwork here in order to figure out a method for how to find kappa by recognizing that that it does represent how quickly the tangent vector turns as we move along the curve, but how can we put it in terms of little t in order to make it something that we can compute? Okay, so the way we're going to do that is we're going to start with dt ds, and we're going to do the chain rule again. So let's start with dt ds. And now we should recognize by the chain rule that that's the same thing as dt, which is good because I could find the derivative of the unit tangent vector with respect to time, times dt ds. Okay, but you can see how we're going to probably deal with that dt ds in a very similar way. That means that we have, I'm sorry, I should modify this. This means it's the magnitude of dt ds. All right, so we're finding the magnitude of this. All right, well, it looks like what we could do instead is we could write this as 1 over, remember dt ds is the same thing as 1 over the reciprocal, which is ds dt. So we could take the magnitude of that times dt dt. Okay, but by properties of magnitudes, that means that we could rewrite this as the magnitude of dt over ds dt. But in addition to that, that means that we could rewrite this again by simply breaking up that magnitude into the magnitude of the top over the magnitude of the bottom. Well, let's keep in mind what dt dt means. dt dt is just saying take the derivative of t with respect to t. So why don't we just write that as t prime of t? And what about ds dt? Well, we should remember again that ds dt is speed, the rate at which our distance changes over time. So ds dt is already the magnitude of velocity. So that means that we now have a formula for calculating kappa. So in order to find the curvature of some object, okay, or some curve rather, we simply take the derivative of our unit tangent vector and divide it by the magnitude of the velocity. So I'm hoping you can see that we're dealing a lot with, we're starting with a position vector called r, and we're taking derivatives of it to get new vectors. But we're combining those vectors and magnitudes in such a way to be able to find information about the motion of this curve. So we're going to be able to compute by getting a numeric value, we're going to be able to actually find how quickly a curve turns as we move along the curve. I know that when we're using a lot of variables and vectors and formulas, a lot of times we don't necessarily see practically what this even means. So we've got a lot of formulas that we've figured out how to find. We've figured out how to find the velocity, magnitude of velocity, unit tangent vector, arc length, curvature, but we haven't really seen practically how we're going to do that. So let's do an example of how to find curvature. Now let's keep in mind that most importantly, we're going to be given a position vector. And this position vector, remember, is just the curve itself that's in 3 dimensions. So this curve, from just being given this curve, we're going to be able to find everything that we need. And the beauty of chapter 3 is that when we actually start with a position vector, it's just a matter of finding derivatives and magnitudes until we get to the result that we need. So to find curvature, let's think about the things that we're going to need. We're definitely going to start with r, and from r, we could then find a vector v. Okay, well that's good. Vector v is important. But for curvature, we're going to need the magnitude of vector v. So why don't we go ahead and find the magnitude of vector v by using the formula that we learned for that. So that's good because we now know what the magnitude of v is, which is going to be necessary in the formula for curvature. But in addition to that, we need vector t. Okay, well that's not a big deal either because if we have vector t, just keep in mind that vector t could be found right now because it's v divided by the magnitude. But that's still not enough because we're still going to need to know what t prime is, which is part of the formula for curvature. Okay, well, it's not so bad. That just means we're going to find our derivative of the vector that we just found. We're going to find t prime. The problem is that we're not quite done yet still, because we still haven't found the quantity that we really need, which is the magnitude of t prime. So now from there, we can find the magnitude of t prime. And once we find all of that, notice that we'll have the magnitude of v, we'll have the magnitude of t prime, which means that the last thing that we can do is find our curvature. This is literally the process you're going to take for all important information involving motion, involving curves. It's just recognizing that we're taking derivatives and applying formulas to find the information that we need. So let's start with that. Let's go ahead and find our velocity. All right, so notice that this is in fact a circle because it's saying that x is changing with respect to t as cosine changes, y is changing as sine changes, and so if x is cosine and y is sine, then that means I'm moving on the unit circle. A just represents how big the circle is. So this is motion on some circle with a radius of a. So what we're going to start with here is finding our velocity curve. So the velocity, remember, is nothing more than just the derivative. It's just the derivative of our position vector. Easy enough. Let's find that. So the derivative of our position vector is negative a sine t in the I direction plus a cosine t, and that's in the j direction. Okay. Well, from there, we're going to need our magnitude. So let's go ahead and do that. So let's find our magnitude then. So our magnitude of v is simply equal to the square root of each of those two quantities squared. So negative a sine t squared plus a cosine t squared. So always do our algebra to simplify to make this look a little easier. So notice that this becomes a squared sine squared t plus a squared cosine squared t. Now don't jump to conclusions yet, because notice that I know that sine squared t plus cosine squared t is 1, but I'm not quite ready yet because I don't see that until I factor out the a squared. And we're now left with sine squared t plus cosine squared t, which now is 1. Now I'm taking the square root of a squared, which is simply a. So I can recognize now that my magnitude of velocity, which is going to be important for my curvature, is simply a. So now that I've got that, I need to find my unit tangent vector. So let's go to that part. So that's not too bad, because our unit tangent vector, remember, is nothing more than just our velocity over our magnitude. The velocity over our magnitude is just going to be negative a sine t over a. That's in the I direction. Plus, well, a cosine t over a. So all we're doing is dividing each component of our velocity vector by the magnitude. And the magnitude was just a. Now keep in mind, a is the radius. So that's pretty cool, because that's showing us that this quantity that we got for the speed of the velocity is just the radius. So we have our unit tangent vector then. Our unit tangent vector is negative sine t I plus cosine tj. Now, before I move forward, I want you to realize something here. If I take the magnitude of this new vector, then I'm going to get the square root of sine squared t plus cosine squared t. The magnitude of t is 1. But obviously it is. That's the whole point of t. T is a unit vector. So if I get this, if I try to compute the magnitude of t and it's not 1, something went wrong earlier. Okay? But we're still not quite done, because if you look back to our curvature formula requires that we find our magnitude of t prime. So we've still got to find t prime. So let's find t prime. So now the derivative of t is equal to negative cosine t in the I direction plus, now the derivative of cosine t is negative sine t in the j direction, which now we can finally use in order to find the magnitude of t prime. the magnitude of t prime is going to give me the square root of negative cosine t squared plus negative sine t squared. But keep in mind that when you're squaring your negative, it becomes positive. So you're still left with the square root of cosine squared plus sine squared, which is 1. So that gave us something else important. It told us that the magnitude of t prime is just 1. Now be careful. The magnitude of t is always 1. Sometimes the magnitude of t prime is not 1. We were just lucky in finding that. But now that we have all that information, we're able to finally find the curvature, which is simply the magnitude of t prime over the magnitude of v. Well, magnitude of t prime is 1. The magnitude of v is a. So we find out that the curvature of a circle is always 1 over the radius. As the circle gets bigger, this fraction gets smaller. But that makes sense. When you've got a really teeny circle, I see that it's going to curve much more. As that circle becomes much larger, with each unit length as I move around the circle, it's not going to appear to curve as much. So the larger the radius, the smaller the curvature. And so this is a way of actually using everything we've seen so far with relation to motion and motion for a curve by utilizing all of the formulas, which are really just a matter of finding derivatives of each of the indicated vectors.